Students, welcome back to the lectures on advanced digital signal processing. So in this video lecture, we will discuss discrete Fourier transform, its application to few of the signals and systems, analyzing some signals and systems with the use of discrete time Fourier transform. We will also see for variety of signals, how to find the output of the systems with the use of discrete time signal Fourier transform. At the end of the video lecture, we will also discuss some of the properties of discrete time Fourier transform, and we will try to see how they can be useful in some analysis of the signals and systems. Hope you are able to see the shared screen. So let us start the discussion with the definition of discrete time Fourier transform. Okay. So let us start with the definition. So if we have a signal x of n, if we want to decompose or identify different frequency content in this signal, in this discrete signal, what we usually do is to find correlation with respect to discrete exponentials of different frequencies. Okay, so these exponentials extend from -infinity to infinity. Discrete exponentials with frequency omega extend from -infinity to infinity. We find the correlation or the similarity with respect to the signal x of n, and for that particular frequency, we quantify as the correlation or the commonness between the signal and the corresponding discrete exponential in x of e power j omega. Fine. Now, this will enable us to have a spectrum of the frequency content of the signal. This spectrum will be complex in nature, having both amplitude or magnitude and phase information in it, because we are finding correlation with complex exponentials here. Further, if you would like to get back the signal x of n from the spectrum that we have, x of e power j omega, which is continuous in nature and periodic in nature with period 2 pi, we take spectrum of one period and find its correlation with the complex conjugate of corresponding exponential signals. Okay, so now these signals are with different time instances and for a particular over all the range of omega from -pi to pi. Okay, so given this, we have seen in the previous class how to find for a given signal like x of n is equal to a power n u of n, its Fourier transform. Here it is explicitly discrete time Fourier transform. We can apply from the first principles, directly substitute this x of n in this expression and simplify further. U of n controls the limits, whereas a can be absorbed in e power a into e power minus j omega, and then you can write this finally as the x of e power j omega for this signal is, okay, this we have seen in the last class. So as you can see, this signal has both magnitude and phase. This spectrum has both magnitude and phase information rate. So now let us take another example. So we have seen how to apply on a signal when this Fourier transform, discrete time Fourier transform. Now we will take a slightly different example where we have a system for which x of n is input and the output of this LTA system, let it be y of n, which is equal to x of n minus 1. Okay, this is simple system where the system, what is the role of the system now? The role of the system is to shift the input by 1 unit, that's all, or n naught units you can consider in general. Okay, so if you would like to consider, we can also consider it as n naught units. ND units. Okay, so now what we wish to do is we want to identify first what is impulse response of the system. Okay, and we would like to apply Fourier transform, discrete Fourier transform on the impulse response so that we can characterize the system frequency content or the system frequency characteristics. Okay, so here we are analyzing the like spectrum or frequency characteristics in of signal. Okay, here we would like to analyze frequency characteristics of system. When we mean by system, system impulse response. Okay, right. So now let us, then this is example 1 and this is example 2. Okay, so now in this case, so how do I get the h of n? By looking at this, will anyone of you will be able to tell what is h of n in this case? What is impulse response of the system? As the name indicates, whenever you wish to find the impulse response, in such simple cases, what you should do is you should give input as the impulse. Okay, so instead of x of n, if I give input a delta of n, what will be the output here? That is y of n, which is equal to h of n, because since I have given input as the impulse in this case, which is equal to input delta of n minus nd. Okay, so here in such simple cases, you can simply find the impulse response by giving impulse as input for the system and looking at the output. So in this case, the impulse response is this. Okay, that is h of n equal to delta of n minus nd. Okay, so now what we wish to do with this, we want to find its discrete time Fourier transform. Okay, this is impulse response and we would like to find its discrete time Fourier transform. What is this discrete time Fourier transform? Okay, that is our question. So this roughly gives like the frequency characteristics of the system impulse response. Okay, right. So now we have a system with h of n equal to delta of n minus nd. Okay, so what is the discrete time Fourier transform? For this, h of e power j omega. Okay, so x of n, we have written x of e power j omega, and h of n, it is h of e power j omega. Through the expression by definition, we can write this as, yeah, and once you substitute in this, what do we get? Hope you might have seen. This is a very simple example which you might have seen before in your DSP course. And this is equal to, this is non-zero only for n equal to nd. So when n equal to nd, the answer is 1. Remaining times this is, so you will write explicitly this one is equal to 1 if n equal to nd and 0 else. Okay, given this, how do I write this whole summation as e power minus j omega nd into 1 and remaining all zeros. Okay, so if you want explicitly 1 into this plus 0 into all that. Okay, summation 0 into e power minus, okay, j omega n, where n not equal to nd. Okay, I have separated where n equal to nd case, this is n equal to nd case, and this is n not equal to nd case. Okay, so this finally explicitly we can write this as, okay, the Fourier transform h of e power j omega is equal to e power minus j omega nd. Okay. So if I wish to sketch its spectrum, can one of you tell how does its spectrum look like? So let this be x-axis with omega here. Okay. And then I would like to sketch from, say, anywhere. Sketch the spectrum. So what is magnitude of h of e power j omega? What is magnitude of this? Cos plus sine minus j sine. So root of cos square plus sine square. So it is 1. Okay. Whereas, so that in that way, the spectrum is all ones. Okay, it extends from minus infinity to infinity, and this is 1. Is this fine? Okay, this is what I have plotted here. Mod of h of e power j omega. Okay, this is what we have plotted here. Now let us see the spectrum of the angle of h of e power j omega. How does it look like? Can you guess what is the angle of h of e power j omega? It is simply tan inverse of, okay, so you can write this explicitly if you want to write. Okay, so cos omega nd minus j sine omega nd. Okay, and then angle of h of e power j omega is equal to tan inverse of, okay, all this, tan inverse of y by x minus sine omega nd by cos omega nd, which with simplification is equal to minus omega nd. Okay, so now how does the angle or the spectrum look like with respect to omega? So if we now wish to plot with respect to, I will plot it here. Okay, with respect to omega, if you would like to sketch the spectrum, sorry, it may be interrupting here, but I'm just going ahead. So how does the spectrum look like? The spectrum looks like, with respect to omega, what is the nature of the spectrum? It is linear. Okay, linear in omega, but not positive direction, but in like the negative direction. Okay, so and then the slope of the spectrum is nd. Okay, so when omega is positive, the angle is negative, and when omega is negative, angle is positive. So it will be like this. Okay, so on, so on. Okay, and so on. Okay, so please excuse me with this. So we will erase this. Since you know this information, okay, I am erasing this. Okay, so this, if you would like to have this is equal to cos omega nd minus j sin omega nd. Okay, so this is, in simple case, we are able to plot them well and show them. So this is angle of h of e power j omega. Okay, so spectrums with respect to omega we have plotted here. Please note that this is referred to a linear phase system. So in fact here, as you can see, this is system impulse response. System's impulse response is this, and system's frequency response is this. Okay, this is system impulse response. So this, what kind of system is this? LTI system. Okay, that's why we are able to characterize it completely by its impulse response and frequency response. Okay, right. So here it is referred to as linear phase system. System with linear phase. Yeah, this is referred to as linear phase. Okay, so in case nd equal to 1, it is purely 45 degrees line. So nd in this case I put equal to 1, but it can be something else in another example. Okay, right. So this is how we characterize the system now using discrete time Fourier transform. In the previous example, we have characterized signal, we analyzed the signal, whereas in this example, we are characterizing the system. Okay? Yeah. Let us see a few more instances of the use of discrete time Fourier transform. See, discrete time Fourier transform, right? So now let us take a system whose frequency, so spectrum is given, or frequency response is given. Let the frequency response of an LTI system is like this. H of e power j omega is equal to 1 for, say, mod omega less than or equal to omega c, some cutoff frequency, and 0 else. Can you sketch this system frequency response? See, what is this kind of system whose frequency response looks like this? Can one of you comment? Okay, so here we have 1 for minus omega c to omega c, and up to where should I sketch this system? H of e power j omega. What are the limits for omega? We have not denoted even here. Okay, so I have written end to end, but what is usually the range in which I should specify the for a discrete time Fourier transform? It is from, what is the nature of this discrete time Fourier transform? It is periodic. It is periodic with what period? With period of 2 pi, and hence sketching it from minus pi to pi is good enough. So if this is the case, assume that this is minus pi and let this be pi. Okay, so this is good enough to sketch this h of e power j omega. Okay, and angle here is 0. So this is so the phase is 0 all through. Here also, please note that though I have written here minus infinity to infinity, we need not write from minus infinity to infinity. So if this is the case, if this is minus pi, sorry, this is plus pi, and somewhere you will have minus pi. Okay, somewhere. Okay, so something like that. Here also minus pi to pi is good enough. Okay, while sketching the Fourier transform or while plotting the frequency response of the discrete time Fourier transform. Okay, because this omega, this is periodic. As you know, it will repeat. This h of e power j omega from again pi to 2 pi, you will have the same spectrum repeating. Okay, that's the nature by definition itself it stems from. Okay, this definition itself makes it periodic with period 2 pi. Okay, so now let us see what is its now given this system. Okay, what this is the frequency response of the system. So what does this indicate? This indicates that the system passes only these frequencies. Say if I have a system, okay, where x of n is given as input, okay, and then the system is h of n, linear time invariant system, and y of n is output. Okay, this system with h of e power j omega, frequency response, its frequency response being h of e power j omega, only passes the frequencies from minus omega c to omega c. Okay, and it doesn't pass the like it completely attenuates the rest of the frequencies. Okay, so whatever is the frequency, whatever may be the frequency content in the original signal, it passes all the frequency content in the range minus omega c to omega c, but completely attenuates the frequency other frequency contents. Okay, so that's what is this. Now let us see what is h of n. So here characters, the what we wish to find is how does h of n looks like. We use discrete Fourier transform or inverse discrete Fourier transform in this case. Okay, so how do I use this inverse discrete Fourier transform? We use, okay, discrete Fourier transform, discrete time Fourier transform. Yeah, so let us do it now. So how do we find h of n given h of e power j omega? So as you know, by definition, it is 2 pi minus pi to pi. Okay, h of e power j omega into e power j omega n. Okay, d omega. Fine. We anyway express the signal x of n in frequency domain. The whole information of signal is again there in frequency domain representation that is shown here. So what we would like to do, if you would like to get back this x of n, what we are trying to do is to use whole in frequency content here and try to assimilate all the frequency content at different instances. Okay, same the and then get back that corresponding signal. So each, say if I have a signal for some duration, each duration may have some contribution here, some contribution here, and so on. So what I would like to do, I would like to take the contribution of the frequencies, okay, at different instances of time, and I would like to get back the signal strength at given instance x of n. Okay, that's what I'm trying to do here. So using all the frequency content at different instances, I want to tell at x n equal to 0 what is that signal. Okay, so this is possible if the uniform the h of e power j omega exists with uniform convergence. Okay, so we will see actually and there is a limit on h of n as well. Okay, so we will see now in this example what is h of n first, and infer few things on the convergence later of the Fourier transform. So let us substitute and solve. What should I substitute here? Minus, anyway, minus pi to pi I have to give, but when I substitute h of e power j omega explicitly here, what is the range I should consider non-zero? It is only non-zero from minus omega c to omega c. So I can, while integration, considering that range is good enough. In that range, what is the magnitude? It is 1. Okay, into e power j omega n d omega. So when I expand this is simply 1 by 2 pi into e power j omega cn minus e power minus j omega cn by jn. Correct? Because the integration when I do, jn will come in the denominator. So this is equal to 2j sine omega cn in the numerator by 2 pi in n into j. Fine. This gets simplified as, so what I'm trying to find here, so I will write with different color just for better visual clarity here. H of n is equal to sine omega cn by pi n. Have you seen this kind of function anytime? This is referred to as sinc function, right? This is referred to as sinc function. If you sketch it, it is not good place to sketch it, but we will sketch it because in this space we can have all the things. So let this be. Okay. This is the sinc function. Okay, it dies down. Okay, so this is 0 and this is minus something and this is plus something. What is this plus? So can you tell what are the 0 points here? That's gone. Let me do undo. Okay, it's okay. So what is plus something and minus something? So I will try to write explicitly. So when this be 0, when this will become 0 first. So when omega c n is equal to, okay, when omega c n is equal to sine g, okay, at n equal to 0, what happens? Sine 0 by 0 form. So it will have its magnitude will be roughly 1. So and hence it is, since it is pi is there, 1 by pi will be its magnitude. Okay, whereas when it is at 0, so it is at pi, sine pi, so is equal to pi. That means the n is equal to, so roughly what is omega c? Omega c is 2 pi by capital N. Okay, assume that omega c is 2 pi by capital N. Otherwise we can see that roughly n equal to n close to pi by omega c. Okay, we'll just leave it here. Okay, right. So you can see, so this is, as you know, this is referred to as sinc function, and this extends from minus infinity to plus infinity. Okay, whereas the time domain function extends from minus infinity to infinity, whereas the frequency domain information is from is only between omega c to plus omega c, minus omega to plus omega c. See, this sudden cutoff in the frequency domain, in fact, is the reason for extending this from minus infinity to plus infinity, right? And to what we usually, if you would like to get back from h of n, say let us now consider starting from h of n, which is sine omega c n by pi n. If you would like to get back h of e power j omega, okay, what is the expression we write? summation over n equal to minus infinity to infinity sine omega c n by pi n into e power minus j omega n. Okay, we go here, the summation is over n, please note that. Okay, see here, how many terms if I add in this sinc function do I get h of e power j omega? That roughly gives an idea on the convergence. That means, see, if I have the in the sinc function, if I just take from n equal to minus m2 plus m, only 2m plus 1 terms. Okay, so the question is, do I get something reasonably close to h of e power j omega? Let this be hm of e power j omega. Will this hm of e power j omega be equal to h of e power j omega? The answer is yes, provided m is reasonably high. So how much high m should be? That we can assess, and that is the that is what is ensured by mean square convergence. What does mean square convergence gives? Say, in case if x of n from n equal to minus infinity to infinity, okay, is less than infinity, okay, then that implies that summation h of, or sorry, here it is all h, right? So we'll write in h, but they are equally valid to x as well. H of e power j omega minus h m of e power j omega whole square over, sorry, this is a discrete variable, a continuous variable, minus pi to pi, okay, d omega, okay, is close to 0. This is the mean square error. Delta, you can consider delta m is equal to this. If I define delta m like this, okay, then what will happen? Delta m tends to 0 as m tends to infinity. Okay, this is being ensured by mean square convergence. Okay, so if m is large, then this condition is also valid. Then it ensures that the Fourier transform of m terms taking 2m plus 1 terms in the summation, even if h of n extends from minus infinity to infinity, okay, taking 2m plus 1 terms will closely approximate the complete Fourier transform. Okay, so visually, if you would like to show it here, let this be h of e power j omega. Okay, so now if I take m terms, I may not exactly get like this, but I may get something like this. Okay, something like this. Okay, okay, here you can see that this goes from minus infinity to infinity roughly. Okay, this goes all over here. Okay, so this goes from minus infinity to infinity, but even if you take m terms, so let the m terms be up to here. This is minus m, sorry, this is minus m, and this is, say, let this be plus m. Okay, even if you take these terms, these many terms, okay, minus m to m terms, even then you can reasonably approximate this discrete time Fourier transform or Fourier representation. Okay, this is being ensured by mean square convergence. Okay, This implies that. Okay. Yeah. Okay. Fine. So let us now discuss one more example and then close the discussion of this video lecture. So this example is slightly different than earlier examples. Okay, in the sense that we will try to analyze the output of the LTA system for periodic inputs. Okay, let this be the input. And what is output? Y of n is our question. Okay. Output of LTA systems for periodic input. Okay, since all the discussion is on discrete, so we are not explicitly saying that it is discrete periodic. Okay. Periodic discrete time signal. Okay. So let us just for, I will just change the color. What is Y of n? That's what we would like to do. Okay. So now, can you guess what property I will be discussing now? So let Y of n, let's go by conventional approach. Okay. H of n into e power. See, this is through convolution. So I have to relate. When I relate, yeah, when I try to find the Y of n in time domain, X of n and H of n are to be convolved to find Y of n. And as an expansion, what can I write? H of k into X of n minus k, k varying from minus infinity to infinity. Fine. So now I will just write it more explicitly with the given input. H of k and X of n minus k is what? E power j omega naught into n minus k. Fine. So I will try to expand it. E power j omega naught. See, this summation is over k. When I expand it, I will get two terms in exponential, two exponential terms, e power j omega naught n and e power minus j omega naught k. So what can I do here? E power j omega naught n can be taken out and this will be minus infinity to infinity h of k into e power minus j omega naught k. Fine. So now, have you seen this anytime? Have you seen this anytime? So you have seen this in the definition of Fourier transforms, discrete time Fourier transform, with the only change that omega naught is more specific frequency here rather than a general frequency that you see there as omega. Okay, so this is h of e power j omega naught. Okay, please note that this is not small difference. This is a very big difference in the sense that this is the discrete time Fourier transform of h of k, yet instant omega equal to omega naught. Only a single value here rather than the spectrum encompassing all values. J omega naught n. This is because you are just sending one frequency as input. So this is Y of n. As you can see, this Y of n, okay, nicely can be written in terms of X of n into H of, or I will write slightly differently, which is agreeing with most of the textbooks, H of e power j omega, where omega equal to omega naught, and when the input is e power j omega naught n. Okay, so and this is x of n. Okay, so the output y of n is equal to h of e power j omega at omega naught. I will just write this as x of n. Okay, this is nothing but x of n. Please note that. Okay, so the output is just x of n multiplied by some constant. Have you seen this kind of, say, whatever we give as input, what I'm getting, say this is input x of n. So whatever I'm giving as input, I'm getting y of n as input x of n multiplied by some constant, where this is complex constant. Okay, so have you seen this kind of similar outputs anytime? Whenever I give an input x and apply some transformation on it, getting the same at the output. You might have seen this in eigenvalue and eigenvector discussions, eigenfunctions. Okay, so this has similarity with eigenvalues, where say if A is a linear transformation or a transformation matrix, x is a vector. Okay, so if this is eigenvector, okay, in that case, what output I expect? Lambda times x. Same x comes as output. Okay, this is in our case, what we have here is, okay, so I am giving transformation to x of n. Okay, this transformation is linear transformation in the above example, eigenvector. Okay, is the signal input I am giving, and then output is some lambda times, this lambda is h of e power j omega naught. Okay, in this case into x of n. Okay, so hope you see. Okay, you see the difference, right? Right. Okay, so now this is referred to as eigenfunction property of, okay, linear time invariant systems. I will write here eigenvalues, eigenvector or eigenvalues. In linear transformations. Okay, so in this case the output is this. Okay, so this can be compared with, or this can be identified similar to eigenfunction. Okay, property of linear time invariant systems. Okay, so which is an eigenfunction here? Here eigenfunction is e power j omega naught n. Okay, fine. So if I give e power j omega naught n, I can directly write output. Okay, so as e power j omega naught n into h of e power j omega at omega equal to omega naught. Okay, so this is this is a very useful property, and this is the property indeed very useful for finding output of any LTI systems. Okay, for periodic inputs. Okay, for any periodic input. This here we have demonstrated with one periodic input, but this is in general applicable to for finding the output of LTI systems for any periodic input. Okay, we'll see in the subsequent discussion. We take just another example before we close the discussion of this class. So let us take slightly complicated x of n now. Okay, a cos omega naught n plus 5. Okay, so now let this x of n be given as input to a linear time invariant system. Okay, h of n, and then we want to find output y of n. Okay, we want to tell what it is. Okay, that's our, and given the eigenfunction property, what I expect is, okay, output of another periodic. What I wish to find is finding response of LTA system for periodic input. Okay, signal. What essentially we do now, given the advantage of eigenfunction property, I would like to use it. So I would like to decompose the input signal in terms of exponentials first. Then I know if it is an exponential form, I can simply say that y of n equal to, okay, y of n equal to h of e power j omega at omega equal to omega naught. E power j omega naught n into h of e power j omega at omega equal to omega naught. Okay, I know this this technique, so I would like to use it here. So how do I do? So let us first decompose. Let's first decompose input signal, input periodic signal, I would say, into complex exponentials. Why are we decomposing into complex exponentials? Because, okay, they are eigenfunctions of LTA systems. To use eigenfunction property otherwise. Okay. Okay, this is why we are doing. Fine. So let us now decompose this x of n into a into, how do I decompose? E power j omega naught n plus phi plus e power minus j omega naught n plus phi by 2. Okay, this is the expansion for cos, as you know. Okay, in a complex exponentials. So I will simplify this. Okay, so how do I write it simply? No, so let us write with slightly different color. A by 2 e power j phi. I will bring all the things that are not complex exponential signal outside, plus a by 2 e power minus j phi into e power minus j omega naught n. Okay, now this is x of n. Now what I will do, I will apply transformation of this on this x of n, because I know Fourier like the complex exponential eigenfunction property. Okay, the constant anyway, when I apply any transformation, remains as constant. I will take it out. Okay, so transformation on the signal, this is using what property I am writing this on? Using which property am I writing this? Taking constant out and applying the transformation over summation using homogeneity and superposition properties, or the linearity property. I hope you are clear. Okay, so now what is the answer for this? This is nothing but e power j omega naught n into h of e power j omega naught. Fine. This constant is anyway constant. Okay. Now plus a by 2 What is this? E power minus j omega naught and input into h of e power minus j omega naught n. Okay, please be very clear here because the input frequency is minus omega naught. So what essentially we are doing here? This is nothing but, okay, this is nothing but h of e power j omega get omega equal to omega naught. Whereas this is nothing but h of e power j omega yet omega equal to minus omega naught. Okay, you should be very clear there. Okay, so that is e power minus j omega. So this is the final expression for y of n. Okay, this is how we can simply apply the eigenfunction property. And however, now can we do further simplification? Is there a possibility for doing little more simplification? So if we know that using the h of e power j omega, if it is symmetric, okay, then what we can say is the magnitude is same for at omega naught and minus omega naught, and phase is antisymmetric. That is just opposite of this. So minus times, say the here phase is negative. Okay, so when the phase here is positive. So using those properties, we can further improve this and write finally. I will leave it as an exercise because of the lack of space and as well as time. Okay, but I suggest you people to figure out and do it for a real signal, real impulse response or symmetric frequency response. Okay, as a into, okay, what do I get here? A into cos omega naught n plus phi plus theta. Okay, so I will write it a little from there. Yeah, I will write it here. Please verify this. I am directly writing the answer here. Y of n is equal to a into h of e power j omega. Okay, magnitude where omega equal to omega naught. Okay, so if you wish me to avoid all this, I will directly write omega naught. Power j omega naught magnitude into cos of omega naught n plus phi. Oh, sorry. Plus theta. Okay, what is this theta? Theta is equal to angle of h of e power j omega naught. Okay, just check yourself. I have written something here, but it is correct, but you check whether it is correct or not again from your side. Okay, so this is how we can write for any periodic function, and for in addition to exponential functions, for cosine functions as well, we can see that it for the output falls in a nice form, and you can see that the input is a cosine signal of omega naught frequency. Output is also exactly with same frequency. Okay, the frequency content of the output doesn't change if it is LTI, linear time invariant system. Okay, because of the property of eigenfunctions. Okay, only the magnitude and phase will change for the cosine function when I give an as it input to an LT system, but the frequency of the output is same as frequency of the input. Okay, so thank you. We will continue the discussion of discrete time Fourier transform properties in the next video lecture. Thank you.